Looks like we're just about there. Welcome back, everyone. And it's official. Looks like we can start. Welcome back, folks. So today we're not doing any extra material. We're not going to move forward into the course. We're just going to be reviewing for our third exam. It's going to start with a problem on linear regression, chapter 7. Chapter 10, I'm thinking between 1 and 2 questions on determining if it's something is a statistic, if it's a parameter, or if you're dealing with an observational study versus an experimental design. But this will be a pretty short section, I'd say, or chapter as far as the exam goes, mostly just conceptual questions. Chapter 12 is our section on probability, and that one is kind of touchy because our probability section is really actually kind of big. So I try to be specific on what kinds of questions we're really going to be asking. And a huge hint is it'll probably be pretty similar to the quiz that we had, quiz number 8. Likewise, chapter 13 is our confidence interval problem, and that one's going to be very similar to quiz 9. So that's where that comment comes into play. If you do solve quiz 9 and send it to me before Monday, I should have ample time to get that graded and sent back to you. So that way you'll know how you're doing on chapter 13 before you do that chapter 13 problem. If you send it to me on Monday, I'll still try to grade it, but Monday is my busiest day of the week, really, Monday and Wednesday. So I might not get it in, but I'll still give it a try. And aside from that, maybe the other announcement is with all the questions that we'll solve today, I'm going to put them into a PDF and just post it right here. It'll be called Exam 3 Class Review Questions. And that's a short set of announcements. Any questions or comments, folks, before we get started then? Okay, well, it's a student-led review, so it's all up to you. I'll let anyone go first, and there can always be like a person who decides the major questions, or we can just take questions from the class in random order. But any volunteers to go first?
Well, we worked on yesterday, won't be on this exam, right?
That's correct. That was chapter 14. But you know, it's all very, very similar to chapter 13, just slightly different formulas.
We go over the example of when we talked about like when Joel is the probability of B if C occurs and like that kind of aspect again.
Absolutely. That particular example, the quiz, or something similar to
Something
it.
similar to that.
Gotcha. Let's see. I should have something in here. Yeah. So let's see. That would be this one right here. Let's give this a try. This is something about having a retirement plan looks like. There's other probability questions, but I think I've given enough hints to say it's probably going to be this one, since that's what the quiz was as well. And let's drop it in here and give it a try. Actually, let me do one other thing. Since we're using this as a whiteboard, it's good to have narrower margins. There we go. So to get started on this one, there's formulas that can help us, but a good idea, just in case there's a trickier question, is really just to start off with a Venn diagram. Doesn't take too much time, and it can double check if your formulas are even correct as you use them. So let's begin by going like this. So there's the entire sample space. We have an event R, it's blue now, an event H. So we make one bubble in the Venn diagram correspond to R. R is having a retirement plan. Another bubble is going to correspond to H, having a health insurance plan. And I guess at some point we've got to read the question. It says a recent survey has shown 71% of all workers in a particular country have a retirement plan. Let's color code that as well. 65% have a health insurance plan, and 49% have both benefits. When they're saying both benefits, they're saying R and H. So taking all that information, the two events that were predefined, we can say probability of R is 0.71. Probability of H is the 0.65. And last, probability of let me try to fix that P. There we go. Probability of R and H comes out to 0.49. That's a pretty significant overlap. That means if these Venn diagrams were actually more accurate, they'd be overlapping more kind of like this, because this is, again, huge overlap. But usually when we write these Venn diagrams, we do space them out because the whole point is just to convey the information. We're not trying to make these bubbles proportionally accurate to the areas necessarily. That would take way too much time. So next thing we'll do is say again. This was from sample exam. That's a good question. Sample exam 3 problems version 1, it says. So next thing we're going to do is there's one value we should put down immediately if you're doing a Venn diagram. And that's this right here, the overlap. So this is probability of R and H. So we put in this location that 0.49 coming from there. After that, anyone recall how we get this value? It's not 0.71. What would we have to do to get it? Exactly. This whole entire bubble represents probability of R. We know probability of R is 0.71, so hammer that into the calculator. But there's extra stuff right here, so you just take away the 0.49. And that's the remaining part, 0.22. So right inside here, let me delete that. We've got a 0.22. And same idea with H. H had a probability of 0.65. So take 0.65, subtract the intersection, 0.49, and we get just a 0.16. Again, the areas here are not quite accurate, but we're just organizing the information. So 0.16 would go right here. And just in case it's useful, it's good to have one last number. Any volunteers for how do we get that last number in the Venn diagram? Exactly. Every number here has to add up to 1. So we could tally the numbers. 0.22 plus 0.49 plus 0.16. There they go. They're tallied. Take 1 minus that answer. And we've got we didn't calculate yet, 0.13. So in this location, this is probability 0.13. But a good question here, just for the sake of the notes, because this is a review problem, is what does that probability really convey? It's outside of both of these bubbles in the Venn diagram, both of them at the same time. So this means that there is a probability neither R nor H occurs. In other words, there's a probability 0.13 that the worker has no retirement plan, no health insurance plan. Let's imagine they're a new hire, they're on a probationary period or something like that. So now that we have an entire Venn diagram going, these parts are not too hard to answer. Part A asks, what is the probability that a randomly selected worker has a retirement plan or a health insurance plan? The or there is just asking us to take this part, 0.22. That's a probability of only having a retirement plan. Take this part, 0.49. That's a probability of having both plans. And this one, 0.1H, that's a probability of having only the health insurance plan. And this will equal, let's see, should be a 0.87, because it looks like we did that tally once already in the calculator. We might as well just grab that value. So it's that in probability. This is kind of a dangerous question though, because the natural thing you'd want to do is if they say retirement plan or health insurance plan, is to take that probability, 0.71, take this probability, 0.65, and write that as our answer. But that can never possibly be our answer because probabilities only go up to 1. They can't exceed 1. They can't go below 0 either. So what happened with this number? When you take probability of R, probability of H, and just add them together, you've counted 0.49 two different times. So you can subtract 0.49, and that gives you the right answer. That's just using the ordinary formula. So if you just are a person that kind of prefers the formulas, you could have gone probability of R or H is equal to the probability of R plus the probability of H minus the probability of R and H, but it comes out as a 0.87. That's just a different option for calculating if you prefer. We've got part A done. Part B is just another related question. It says, what is the probability that a randomly selected worker does not have a retirement plan and does not have a health insurance plan? That one's kind of tough without a Venn diagram, I'd say, in my opinion, but anyone see what the probability is? Exactly. When it says no health insurance plan, no retirement plan, it means you're in this region. Everything outside of both of those bubbles in the Venn diagram. And so we just grab that to 0.13. You can get it from part A as well. It's just the complement rule really in play. If part A is having a retirement plan or a health insurance plan, the complement to that statement is saying neither a retirement plan nor a health insurance plan. So if you prefer the formula in part B, it was really the complement rule. Part B is 1 minus the probability, R or H, which means it's 1 minus 0.87. And we're back to 0.13. So that's about how our real exam 3 question is going to go. I've kind of decided that since I've hinted at it so many times, I don't think I can back out of it now. But it's not going to be anything too crazy like you might see in the homework. Think of the homework as where those are some of the tougher problems. And if they are exceptionally tough, don't hesitate to ask me to take a look at them at the start of class. That'd be a good use of class time. Maybe not so much for an exam review because we're focusing on the exam questions in particular. But that's one down, folks. Others that folks would like to take a look at. And don't hesitate to call it out or put it in a chat as well on Zoom. And if we're working a problem and a problem comes into mind, shout that out and I'll just put it on this notepad right here and we'll go down the line. Yeah, absolutely. So chapter 7 is, I feel like a problem we definitely have to do, right? We've got one here dealing with some kind of bird, looks like. Should we try this one or did you have a different one in mind? All right, let's give this a try. I'm going to take this in a series of screenshots so that I can move through all the different parts. And here's our next question. Let's put it on the next page though. So in a study of the tufted titmouse, some kind of bird, an ecologist captured 7 male birds, measured their wing lengths and other characteristics, then marked and released them. I think we saw this problem before, but we didn't do the full regression on it. I think we just did a scatter plot and correlation on it as a quiz problem. It goes on to say, during the ensuing winter, he repeatedly observed the marked birds as they foraged for insects and seeds on tree branches, noted the branch diameter on each occasion. So that's this right here. Looks like that's the response variable. And calculated from 50 observations, the average branch diameter for each bird. So this was after they landed 50 different times and they averaged the diameter of all those branches. Someone's working really hard for this problem, you can imagine, really hard. But it's got to be someone who cares a lot about these kinds of birds. And they say the results are given in the table below and a scatter plot. It's about what we would say. The bigger the wing length, the bigger the bird is. And that means the bigger the branch they feel confident of landing on. So it's the kind of picture you'd expect. But they want more precise information, so that's why they're doing a full regression. It says, give a rough sketch of the least squares regression line on the scatter plot provided above. If you do something just random like this, you got it. That's a rough sketch. It doesn't have to be perfect. The only way you could lose points on this is if you did something kind of wild like this. There's no way that's the regression line, right? It's not attempting to match up with any of those points. You do something like this, for example. This has happened. That's one thing we can't do. That'd be great, though, if we could come up with a line that just goes and ricochets around the points. But that's not what regression's trying to do either. So just try to make one line that seems to get closest to as many points as possible, and you've got it. You shouldn't work too hard or worry too much. Does that make sense, folks, on that first part? Okay, this line that we just drew, we often write as y equals a plus, oh, hang on, that's what the calculator says. Let's go with that. Our author says it's slightly different, but you know what? It's easier to just go with what the calculator says, in my opinion. So let's keep it this way. Sometimes we put a y hat to emphasize it's a predicted value, but that's a stylistic choice if you put the hat on it or not. So let's take a look at part B next.
Is that between P hat, I guess P hat is a predicted value or is P is the?
Yeah, it's the same kind of idea, exactly. Yeah, the P hat is the value that's trying to predict the true proportion P. So let's grab this part. We want a least squares regression line next. It's kind of weird. There's nothing to do in part A, but we really did it up here. This is the fun part where we now have to grab our calculators and start by importing the data. So hit the stack key to start, hit enter right away since we need to edit our data. Always good to remind yourselves this is a quick way to clear the variables. F arrow, so this is highlighted, hit clear and enter. It could save you a full minute, and a full minute on exam setting is sometimes a long time. So hit clear again, enter, and now let's do the careful work of putting these in bit by bit. I'll go quiet while we do this. I should remove that though, sorry. Okay, I think I've got it in. Anyone need any additional time? Okay, next step is after you've got all the data in, hit your stat button once again, right arrow to the calculate tab, and go down until you see the A plus BX. Skip past this one, AX plus B, not because it's wrong, it's just unneededly confusing. We don't need that one. So if we go this route, this is more closer to how our book formats the regression line equation. Hit enter on option 8. Your calculator should look like this with L1, L2. If that's all the case, hit enter again to calculate. And this is the information it gives us. This is a good screenshot to take because the tricky thing about the calculator at this stage is it gave us the regression line, but we have to extract that information and write down what it really is. So we'll go y equals, or y hat if you prefer. It's going to be the A coefficient first, and our A coefficient is negative 5.66. Then we'll go either plus or minus. It's going to be a plus because B is positive. So plus 0.085x. So that's our regression line equation. Loads of mathematics goes into doing this, but our calculator doesn't really have too much trouble. It's producing the equation for this line right here, and This value is the slope. This value here, just the integer part, not the variable x, is, or hang on, my apologies, these are backwards. The first part was the y intercept. That's kind of embarrassing, sorry about that. And the part multiplying x, that's the slope. Well, part B is done. Anyone getting anything slightly different in the calculator or any questions about those steps? Okay, again, these are pretty good steps to just put down on a sheet of notes, just in case your brain just decides to forget that during exam setting, stuff like that. It's good to have extra protection. So next step, or next part, C says, give a practical interpretation of the slope using the context. This one's a little bit more tricky, so let's take our time with this. When it says using the context, we have to talk about wing length somewhere, and we have to talk about branch diameter somewhere. And the slope is just rise over run. So if you take any point here, move right by 1 unit and up by 1, that's conveying what the slope is. So moving right is the explanatory variable unit, wing length. Moving up is the response variable, branch diameter. So we can say at this stage, B, which is slope, is going to be equal to this value, 0.085 divided by 1. So we're converting it into an actual fraction. And by doing that, recall it's, again, rise over run. Run is a horizontal direction, so it's 1 millimeter wing length. The rise is the vertical direction, so this is, let's see here, centimeters, branch diameter. And writing all this stuff up is not the answer to the question. That's kind of unfortunate. It's just here to help us get to the answer. So think of this as the steps in the middle, and our actual answer to this goes like this. We focus on the denominator, we're thinking of this diagram here, we're moving right, and then we're saying just how much we go up. So we'll say for each additional millimeter of wing length, the branch diameter, we'll say increases only because it's positive. Increases. Sorry, say again. Yeah, or rather y over x. So it's the change in y divided by the change in x. You know what, that's probably good to add to the notes as well. So this is always rise, so it's the y variable. It's always weird, that pencil tool sometimes lags. I don't know what causes that. And this is the run, which is the x variable. So we're saying if the x variable increases by 1 millimeter, well then the y variable, branch diameter, should increase by 0.085 centimeters. Barely anything at all, but there is a difference. So we'll say the branch diameter increases by 0.085 centimeters. Well, we did it, folks. Any questions about the write-up here for the interpretation?
So the line that we draw for A is supposed to have like supposed to have a 0.085 rise.
Yes, it's supposed to have that same exact slope. I mean, it won't because we freehand drew it, but it's actually a lot of times pretty close when you do that just by hand. Yeah, so this line is meant to represent that same exact slope, that same exact y-intercept. Other questions at the moment? Okay, that's one interpretation down. Let's screenshot this just so we can remind ourselves of the context as we go. Let's take even a bigger screenshot, why not? Let's go down to here so we have the actual model. One thing that's always tricky about these classes is trying not to scroll up and down incessantly, because I bet that is just kind of not a good experience. So next part, give practical interpretation of, oh, that's part D next, rather. We're wondering if it makes sense to interpret the y-intercept of the least squares regression line, and if so, we'll interpret it. These, in my opinion, are sometimes more tricky than even interpreting the slope. So let's think about this again. When they're talking about the y-intercept, they're talking about this part right here, negative 5.66. You plug in a value of 0 for x to get that, and that's already a big hint. Let's say here, just for the sake of the notes, at a y-intercept, x equals 0. So we have to ask ourselves, could x equal 0? What would happen if x equals 0? In other words, yeah, that'd be a really sad bird, and we'd hope that someone takes care of it. They've got no wing length at all. That's probably not in the spirit of this problem, right? They're not going to perch and fly onto a branch without any wings whatsoever. So x equals 0 makes no sense in this context. And if that's the case, neither does the y-intercept. So we'll say here, since we're doing the explain y part, x is wing length, x equals 0 is let's not say it that way. Let's say it does not make sense. And so we cannot interpret the y-intercept. And we wouldn't want to either, because all of our data goes from 79 to about 84. Putting x equals 0 inside there is massive extrapolation anyways. It wouldn't even make sense. So the intercept is important. It builds the line, but it's way out of the scope of our data if we try to throw a 0 in there in the first place, even not even thinking about the context. Well, any questions, folks, about that one? Oh, it's always kind of tricky to see what can move down. Let's try the next one then. We're at part D, and coming up next. Sorry, my computer just froze for a moment. Is what is the predicted branch diameter for a wing length of 81 millimeters? I'd say this is kind of like the fun part of the problem, because we made the model. There it is down below. We've done some interpretations about the slope, the intercept. Now we're just using it. When it says a wing length of 81 millimeters, they're talking about the explanatory variable, and that means they're talking about x. Let's say if x equals 81 millimeters, that's a pretty big, well, no, that's kind of average, maybe below average. If x is 81 millimeters, then the predicted branch diameter, that's y hat, will be equal to, we go down and take these values, negative 5.66 plus 0.085, and multiply that result by the 81 millimeters in the problem. So that's all we have to put down. We do have to calculate it, so let's do that as our next step. We have negative, don't forget to lead with the negative button here. It's kind of annoying with these calculators. Negative 5.66 plus 0.085 by 81. So this gives us a predicted branch diameter, 1.225 centimeters. So what we've done is we've taken a data value, right at 81, we went up to the regression line, and the output was the 1.225. Looks pretty plausible based on how we drew our line even, so that's kind of cool. Any questions at all, folks, getting that computation? Okay, so part E is just using the model that we produced. And let's see what goes on in the last part here. Probably, oh, no residual. That's kind of nice. It's asking, explain why we should not use the least squares regression line to predict a branch diameter from a wing length of 100 millimeters. It's a kind of an interesting question. I think we hinted at this a little bit when we were in chapter 7. And there's one word that kind of explains why we really shouldn't. Confusing though. I mean, we just put 81 inside the model like this. Nothing actually prevents us to take 100 millimeters and plug it right in there, get another answer, except I guess you could say ethics. We really shouldn't. Anyone know why we shouldn't use a model at 100 millimeters?
Does it kind of go back to the, I can't remember what it's called, but the IQR rule where it's more than 1.5% of the.
It does, yes. It's not necessarily using the IQR rule exactly, but it is the same kind of concept. The trouble with the 100 millimeters and what the IQR rule would say is it's an outlier. 100 millimeters is way out here. I don't know if that's accurate. I think it's even further to the right potentially. And there is no data whatsoever. So something's fishy about that 100 millimeters. On one hand, it's extrapolation to put that into the model. We really shouldn't. Let's say that is our official answer. 100 millimeters is far outside the range of X values. X values just to say the range for your X-axis values that we're plugging in. And so this is extrapolation. Oh, geez, let me move that down. There we go. And so this would be extrapolation. Sorry, I have to sound that one out. That would be extrapolation, and the result cannot be trusted. Not until maybe we get more data where birds are around 100 millimeters in wing length, or maybe we just realize that this one at 100 millimeters isn't the right bird in the first place. Someone might have made an identification mistake, and that's why it's an outlier. Might be a totally different species of birds in the first place. If that's the case, we definitely shouldn't use a model. The model is for one specific bird species, not anything else. But looks like we did it, folks. That's the rundown of a regression analysis kind of a question. Any questions about any of these parts here that we went through? That is a great question. I think for me, because I didn't put on this review guide whatsoever, I'd say that's a no. I'm not going to focus on the residuals for this one. And even in the question itself, I put a residual question on here. It'd be a little bit awkward because this part was 81 millimeters, but it's not even in the data in the first place. For a good residual question, I should have asked a prediction on one, and then we calculate the residual on it. So yeah, it looks like residuals won't be part of this exam, mostly something that we got through in the homework and potentially a quiz problem as well. Well, other questions, folks, on this problem here or other problems to take a look at? Let's see, we've done probability, we've done regression. That leaves behind, we could do a confidence interval. How's that sound to folks? Might as well, that's a big procedure. And we've got a couple down here. So I'll leave it up to the class. This one is do's and don'ts for job seekers on social networking. We have something about kids getting drunk in middle school. That's exciting, I guess. So your pick. Should we take a look at social media or middle school shenanigans?
Middle school.
Okay, let's take a look at this. I think this is real data, by the way. A National Health Organization warns that 30% of middle school students nationwide have been drunk. I think they're meaning at least once. And by drunk, I'm not sure if they mean buzzed or not. We'd have to buy the article and read it. Concerned, a local health, this is the made up part of the problem, it looks like. A local health agency randomly and anonymously surveys 110 of the 1,212 middle school students in its city. Only 20 of them have reported been drunk. So that's interesting so far. Let's break down this problem, starting in part A. Probably somewhere in California, I'd imagine. Those schools have humongous campuses. So with what we've got so far, let's start recording some information just by reading the context again, which is a good exam strategy. I'd read this context maybe at least 3 times on a real exam. So it says 30% of middle schoolers nationwide have been drunk. That 30% right there is really dangerous because it's a value for a parameter, and it's a value for a parameter for the entire nation. That's not our population though. Our population we're concerned with is this specific middle school. So what we're doing is comparing the data of the middle school against the national data. So watch out for that value right there. So when we go to describe the unknown parameter, P, let's mention up here, P is not equal to 0.30. It's targeting the wrong population. We need to narrow down to this. Let's see. Some particular middle school students. Oh, I think that makes sense why it's so large. I think they're referring to multiple middle schools, all of them in a particular city, by the way this is written up.
So is the population every middle schooler or the one in that city?
I think it's that specific city, yeah.
But it says we have 30% of middle schools nationwide.
Yeah. So if we look at everyone in the nation, 30% of those have been drunk. So now we're saying we go to a smaller population, all the middle schools in a particular city.
There's 2 populations.
Yeah, that's exactly what's going on here. And that's tricky enough. Let's actually mention that in the notes down below here before we get too far ahead. So we have one population is the entire nation. The parameter is equal to 0.30, but our population is all middle schoolers.
So we put all 112 students.
Well, this would just be the sample. We don't actually know the population size in this problem.
Would the sample be 100?
It's not 110. That's going to be the number of successes in the problem. And the 110 is being drunk. That's the success in this situation.
Only one.
Oh, you're right. What am I looking at here? Anonymously surveys 110 of the 12-2 middle school students. Yeah, it looks like that's the sample. That's the successes. That's the population size. Sorry about that. I should have read this question a little bit more carefully before launching right into it. Does that make sense with that so far?
So in our answer, would we be able to write our population of 1,200 students, or would you just want to leave it all middle school students?
We could say either way. We'd be referring to the same number. So we could say our population is all middle school students. Like you said, there is 12 of them in this city. That's definitely pretty tricky. Thanks for those questions. I think I definitely misinterpreted when I looked at this right here, thinking of that successes, that is the sample size. So really, before we even get into part A, it's always good to again read the context a couple times. Let me read it again myself. Concerned, a local health agency randomly surveys 110. I should pause right there and write N. Our sample size is 110 students. 21 of them reported being drunk. We'll say right here. I can't quite fit that in. Let's just say it this way. 21 successes. and the problem. And now success is saying that you have been drunk as a middle school student. That's just weird to say that over YouTube, but we know it's statistics. That's just the weird language we have. And now we're ready to write out P. Any volunteers for writing out this statement here? I'll start. It goes true, your choice, proportion or percentage. I'll go with proportion this time. Of all, well, we have a couple options this time. We can say all middle school students in the city or all 1212 students. Really up to you. Let's go with all middle school students in the city that. Now we have to say one last thing. We have our parameter. Anyone see what the missing part is? Exactly. We'll say have that report having been drunk. Good call. So true proportion of all those 1,212 middle school students in this city that reported having been drunk. So we've got a parameter down. Sometimes, again, that's where most of the fighting goes in this kind of problem. If you make a mistake on part A, but you still use the same description in your overall conclusion, there is not double jeopardy. So you might lose points in part A, but if what you said here is consistent on the end, you won't lose points again. So let's go off now to part B. We're asking, are the conditions for met for the large sample confidence interval? And here we're not going to try to go through every single one of those conditions. We're mostly majorly looking into, do we have a random sample? And is the sample size itself going to be large enough? But look here, I think we said it's unknown if the sample is random a lot in our lecture notes, but this one said it was random. So we'll say here, on condition 1, the sample was selected randomly. So we didn't pick like the 110 valedictorian students or top grade students in this middle school. That would skew the actual results massively. You have to pick them randomly. So these 110 students represent the overall population size. Then condition 2, we have to check successes and failures. We just need to write it down. So we have 21, which is greater than or equal to 10 successes. Put a little check there to say that part of the condition's met. The sample size is 110, so take 110, subtract the number of successes, and that's our number of failures, 89 of them altogether. And 89, which is greater than or equal to 10, failures, we'll check on there again. And so we can say the sample size is large enough and conditions are met. So we can be confident when we go to write out our conclusion that it's a pretty strong looking conclusion, having met both of those conditions there. That's a lot of writing, but now we get up to the fun part of the problem. I think we want a good screenshot that goes like this. We're going to need this information for a moment. Now let's grab the next part. So here's part C. We're going for 90% confidence interval. For the unknown parameter, round to 4 decimal places. One comment I want to make on this particular problem right here is, usually I break this up a little bit more. For example, on this quiz right here, which is more similar to our actual lecture notes, I'd say, your problem is probably going to start off by saying, calculate this first, then calculate the standard error, then calculate the confidence interval. So it'll be broken up a little bit more on a real exam. Let's go in the same order, do the sample proportion of successes. So for the confidence interval itself, we start with p hat. P hat is the number of successes divided by the sample size. So it's going to be the 21 successes we identified, divide by the 110 students. Our end answer is going to be rounded to 4 decimal places. So let's round this to 4 as well. If you want a very accurate answer for, say, my stats lab, probably round everything to 5 decimal places, and then your final answer to 4 decimal places, just out of safety. But it's less of a concern on an exam situation, since a real human is grading this. So take 21, divide by 110. And looks like a repeating decimal. That's kind of cool. 0.1909 is what I'll report to 4 places. 0.1909. The next component we need is the standard error, SE of p hat. This one goes by the equation square root p hat, 1 minus p hat. We're dividing next by a sample size, 110. Now let me write that down as a formula first, since the rest of it is as a formula. Now, next part, go 0.1909. That's taking the role of this p hat right here, then multiply by 1 minus the same thing, 0.1909. We're dividing by a sample size of 110. I think we're done with this as a screenshot now. And let's write this out one more time. Show this on the exam for partial credit. That's an important statement because, again, it's easy to just miskey something. I'm sure you've seen me do this hundreds of times in class. And if I put in a 0.9109 just by accident, I'm going to get a completely off answer. I'll have no idea how accurate your thought process was unless you put all that down. So that's our way of giving partial credit. So let's calculate this. I think this is like our 15th time doing this kind of computation. I'll hit the second and square root button to throw it all in one line. Tap in 0.1909. A parenthesis and 1 minus the same value. 0.1909. Immediately hit division after you close a parenthesis. Watch out for that. If you divide now, you'll get the wrong answer. And you're dividing by 110. So here we have it, folks, to 4 decimal places. This one will round to 0.0375. Let's record that answer next. Any questions at all getting our standard error? Okay, once we've got the standard error, we pretty much have everything. We take this equation, p hat, plus or minus a z star, multiplied by a standard error of p hat. So we've already got this value. We have this value. The only thing we haven't resolved yet is what is the critical number? It's going to correspond to 90% confidence. So in this problem, z star is going to be, I forgot. Let's go take a look. So the next thing you definitely want to include on your page of notes is, let's go and dig out chapter 13. In chapter 13, there's this all-important table right here, which solves lots of stuff. It's this one, the table for your critical numbers. We can't do this in chapter 14, but on this exam, we can. So let's take advantage of that. It saves a lot of steps computing z star. Let's leave this here just as a screenshot as a reminder. This is useful in the notes. So at 90% confidence, z star is 1.645. So we've got now a z star. We're just going to plug everything into this formula right here. So this becomes, let me just rewrite it here so we don't have to try to squeeze it in. Okay, here's our next attempt at this. For p hat, we produced a value 0.1909. Then go add or subtract. For z star, we table looked up 1.645. And last thing, standard error p hat, we calculate at 0.0375. And by the way, if something happens, maybe you just forgot to put this on your note card or your page of notes for the exam, or maybe it got wet, something happened, dog ate it. It's pretty fast to calculate. Let's just show it just this once. Go into your calculator, hit second, bars. To calculate a z star, it's inverse norm. For area, same exact formula we used in chapter 14. Take 1 minus confidence level as a decimal, 0.90, divide by 2, and that's all you have to do. Just make sure mu is 0, sigma is 1, and enter a bunch of times, and this is what you get. Negative 1.6448. So this value has been rounded, and your calculator produces the negative value. Either way, it's good to have the table to just look it up, so you don't have to waste that time on an exam setting, but you can calculate it pretty rapidly. Last thing we're going to do is just plug the parameter right here and actually do that computation. Feels like the AC is running. This is really weird. I don't know how they designed this building. Has it? I see. Yeah, they're probably have to try to spend money to fix it again. So back to the calculator, put this in once, 0.1909 minus 1.645 times 0.0375. So that's our lower bound since we used minus. We're rounding this one to 4 decimal places, 0.1292. That means we're halfway done in a certain sense. Does that look right to folks on that number? Okay, now we just reconvene back to the calculator. For the folks using TID3, hit second, enter key to get your last answer. For people using the TID4, it's usually simpler to up arrow, hit enter and paste it down like that. Then left arrow on either calculator to that position. We're right here in the calculator, so we overwrite with a plus. And now that's our upper bound, 0.2526. So in a certain sense, this is kind of interesting. Remember, P is the true percentage or proportion of these middle schoolers that have admitted to being drunk. It's as low as about 13%, as high as about 25%, but the national value is 30%. That means the school is kind of special in a way. It's below the national value based on a 90% confidence interval. A little shady though, right? 90% made our interval kind of unnaturally narrower. We're less confident with a narrow interval, but at least we've got something that we can give people as a result. We're going to have to be honest when we go to give that result. Oh, sorry, I'm not sure where I'm scrolling. That's going to be the next part. Here, let's see. Yeah, give a practical interpretation of the confidence interval using the context. There's more parts on this document, but I'm not going to ask these last conceptual questions on part E or part F. I'll leave it up to the class if you want to pursue those, but probably pursuing another question might be a better bet. Let's go down here and now give that practical interpretation, which means we need to go over here, grab our parameter. Just as a reminder, so we say the right thing. And the conclusion goes basically the same each and every time. We change the first step or the first statement and tune it to what the confidence was. So we'll say with, this is 90% confidence. It made our interval narrower, but at least we're mentioning the confidence. So that way we're being ethical at the same time. With 90% confidence, I'll go with the percentage. The true percentage of middle schoolers, I'll just say middle school students in this city that have been drunk, we now go and say is between 12.92% and 25.26%. So that's our conclusion. And, you know, there's not a follow-up question along with that confidence interval, but it's worthy to think these last extra thoughts. Let's type it out just so it makes it look like just extra remarks. This shows that plausible values of P, our parameter, is below the national result of 30%. That means this middle school is pretty exceptional, but maybe not by a lot, because remember, this is only 90% confidence, and the upper bound is close to the national level either way. But still, it's positive news for people who administer that school. Any other questions, folks, on getting through that full confidence interval? Okay, because I'm a fan of partial credit, just another reminder, on the real exam, it's just like the quiz. This will be one part, this will be another part, and this will be another part, in other words. Not necessarily parts A, B, and C, but you get the idea. I'll try to break it up to help just balance things out. Well, it looks like we still have about 13 minutes and some change. Any other questions folks would like to take a look at? Yeah, absolutely. Looks like the last things we haven't seen yet on this review. And it looks like chapter 10 has something about 401k distributions, cocaine addiction, and looks like something with a Gallup poll survey. Any volunteers for a question to pick out of that list? Okay, it says, let's just take the screenshot of it. I think we can just take the whole problem since there's not dozens of parts on this one. Okay, I like how the statement starts on this one. Something that is, think about obvious to everyone. Cocaine addiction is hard to break. I agree with that. So they've already got me. It says next, addicts need cocaine to feel any pleasure. So perhaps giving them an antidepressant drug will help. This is an old study. I think this problem is based on. One study randomly assigned 72 chronic cocaine users to take either an antidepressant drug called desipramine, or they gave them lithium. That's weird. That's, I think, an antipsychotic medication. And some of them got a placebo. Imagine a friend or a cousin is a chronic cocaine user and they got the placebo. They're probably going to know right away, right? Or lithium, that's going to be really weird, but the study really was ran. This is kind of crazy. They tell us lithium is a standard drug to treat cocaine addiction. I actually didn't know that. And 1/3 of the subjects chosen at random received each of the drugs. First, we want to describe the population on this one. What would you all say the population should be for this problem? Yeah, so we could just say cocaine addicts, and we could just say briefly just all cocaine addicts, right? They would fit in the study whether they want to kick their habit or not. We're just wondering if we gave them those drugs, would they not need cocaine as much? So if you said just cocaine addicts in general, every single one of them, I think that would be just fine. Some people might say chronic cocaine users or cocaine addicts who are trying to break their addictions are just fine as well for answers. But let's leave it just like that and go off to part B. What would you say the sample is on this one?
Is 72 people assigned?
Yeah, right here. They have 72 chronic cocaine users. They're probably broke, but that's our sample. The 72 cocaine users. I guess it's rude to call them addict, I guess. So we're calling them users. Next is part C. We're wondering, is this an observational study or an experiment? Hard part about it is we have to explain our conclusion. So how do folks feel about this one?
It's an experiment because they're splitting up the sample into 3 different groups and comparing the results between the two.
Exactly. This one's an experiment for exactly what you said. We could say briefly, there was 3 treatments, one of them being the placebo, that's the control group. That's actually not enough for an experiment. So the other key element that you mentioned is they were randomly assigned to take one of those 3 different things. So there's 3 treatments, and the 72 subjects, the cocaine users, were randomly assigned to the treatments. The random assignment there is really essential. You can imagine you've got 72 people in a room. You can't say who wants the placebo group. You're never going to get any reliable results out of that whatsoever. So it has to be by random. It has to be a blinded study too. You have to make sure the people who get a treatment don't even know what the treatment is. Because once again, you can't tell them it's a placebo. But then you might start to wonder, was this an effective study? Because if you're a chronic cocaine user and you give someone a placebo, they're probably going to tell right away they're in a control group. Nothing feels right. They feel terrible. They're not receiving lithium. That was a standard drug. And they're not getting the experimental drug. So probably both of those people realize something is up in this kind of a study. But we did it, folks. That's about what the exam question is going to look like for chapter 10. Really fast on population versus sample, something about whether we have an experiment or an observational study. And for anything else here, there could be questions that come up about parameters or statistics. Should we try one more going along those lines? Okay, let's maybe just grab this one. You know what, they're fast. Let's grab them both. Why not? So last 2 questions here. On number 33, Gallup poll conducted a telephone interview with a random sample of 1,069 adults, 18 years and older, living in all 50 states and the District of Columbia. It looks like the population was just the United States of America. They asked them, what would you like to see government leadership do in the fiscal cliff negotiations? I stick to their principles and beliefs on tax increases and spending cuts, even if no agreement is reached by the January 1st deadline. Gotta love politics. Or 2, compromise on their principles and beliefs on tax increases and spending cuts in order to reach an agreement by the January 1st deadline. That's a heck of a poll. And they said 70% of the Americans say leaders should compromise. Question for the class. Is that 70% a statistic or a parameter, and why?
Because it's the answer, not the population of the sample, like of people who did the survey.
Exactly. It reports 70% of the Americans, when they say of the Americans, that was the 1,069 adults. But that's obviously a sample, right? That America is a huge place with millions of people. So we can say statistic, since 70% is describing the results of the sample. And looks like number 34 comes up back up again. 34, the problem that we just did a confidence interval on, is bringing up to 30% once more. This one is a parameter. I mean, it's got to be, right? If I gave a question on statistic, the other one's probably a parameter. result. But any volunteers for what makes that a parameter?
Describe the population as a whole.
Exactly. So this is a parameter. It may not be the parameter describing the actual population of the study, the 12,012 middle school students, but it is still a parameter because it is still describing a population. So here we'll say 30% is a parameter since it describes the population of the entire nation. USA, in other words. Oh, looks like I missed a chat. Sorry about that. And looking at the clock, yes, that was a statistic. I think you're referring to that one, I think. Sorry about that, Brandy. Well, any other questions, folks, on getting through these? Okay, well, we pretty much ran out of time and we've almost ran out of questions, but I'll go to the minute. Any last questions folks would like to discuss?
When we're answering a problem on the exam for conditions for large sample confidence intervals, you have to clarify that we know the number of successes, correct? We can't just put like what the number is minus 10. And then the answer to that, we have to put what the number is, the successes are minus 10, and then put it in the.
Yeah, so you have to actually put in that number right there and then that number there. That's the major things I'm looking for. Yes. Other questions at the moment? Okay, well, I think we have a good stopping point then. When we come back next Monday, we'll just be going over the exam. It's going to be about 5 questions, same kind of stuff that we've been going here. Really, the only thing that's kind of a departure is problem number 38. Once again, it's going to be written more in the style of the quiz, broken up into more parts. Well, have a great weekend, folks. And just one more reminder, if you solve quiz 8 early, I'll make every effort to grade it and return it to you so you get extra feedback on if you solve quiz 9 early is what I mean, for chapter 13. Yeah. Well, have a great weekend, folks. Try not to work too hard, but if you are, then we'll get through it together.